So last week before fall break, we were talking about reasoning. I went through a last part of reasoning rather quickly on causal inference. So I'm going to just run through that very quickly. And I'm going to wrap up reasoning and we're going to jump to generation, which is the next technical challenge. So the reason I'm going to go through causal a bit more is because I feel personally that it's a very, very big area of machine learning nowadays, bridging deep learning methods, which are learned fully on data with causal inference mechanisms to make sure they're more robust to causal interventions. So just to recap very quickly, what was reasoning? We saw this very cool setting where you have two variables, x and y, and you want to generate a joint distribution between x and y. You could do a couple of things, right? You could first generate x from a random Gaussian, and then you can start transforming y from x. That gives you a joint distribution between x and y. You can also generate y first from some random distribution and then infer x, or you can generate some joint random variable z, after which you infer x and y both from z. And these are different ways of generating the same underlying distribution between x and y, right? The joint PDF looks the same. But however, if I want to intervene, if I want to say I want to set x equal to 3 and look at the marginal distribution of y, given the fact that x equals to 3, how can I do that intervention on these three different snippets of code? For the first one, you see that you start drawing x from random, you insert x equal to 3, you fix x as 3, y is also naturally going to take on whatever value y is when x is 3. But for the other two snippets of code, if you start setting x equal to 3, the value of y when intervening on x equal to 3 is different from the first case. Right. And again, we saw these distributions, and this is essentially what we call do calculus in causal inference or intervention. Intervening on x equal to 3, that's the do x equal to 3 conditional, and seeing what the marginal distribution of y is given that. And again, we saw that this is actually very different from the actual true marginal distribution of p of y given the fact that x equal to 3. And the main reason here is that you can look at these causal diagrams, your graphical models, how x and y are generating and affecting each other. In the first case, you saw x causing y. In the second case, you saw y causing x. And in the third case, you saw z causing both x and y, where z is this common cause. And therefore, when you set these interventions of intervening and setting x equal to 3, what you're essentially doing is that you're removing all the in edges into x in this graphical model. In the first case, there's no in edges into x. X is just a random variable not caused by anything else. Intervening on that is essentially the same as the actual marginal p of y given x. For the other two, there's in edges into x, either from y or from z. Intervening on x essentially removes these in edges, right? And when you remove these in edges, x and y are no longer connected; they're independent. So the probability distribution of y, given that you intervene on x, is just the distribution of y itself. So that's why the whole foundation of causal inference, at least one of the big foundations of causal inference, is the fact that you have to intervene. You can't just observe this from joint distributions of data, but you have to intervene on one of the random variables. But typically intervention we've seen is very difficult, right? If I want to ask a question like, does some treatment X treat disease Y that a person may have? It's very hard to estimate this intervention, right? Because once you give this treatment to a person, you can't really reason about the case where you had not given a treatment to the same person. And if you give that treatment to one person and not a treatment to some other person, there's so many possible confounding variables between the two different types of people. So basically requires answering, like, all else being equal, what would have been the patient's outcome if they had not taken a treatment when they actually took the treatment? So again, all these graphical models are very useful ways of reasoning about this, where x is your actual treatment variable that causes some outcome, and you want to test the causality from x to y. Typically, we see z as a confounding variable, right? That's another word people typically use in deep learning, where z is some confounding variable that causes both x and y. So even though you observe some causal or distribution between x and y, you're not sure if it's actually x causing y or z causing both of them. And again, lots of work in causal inference. One good reference is Judeus Pearl's book on causal inference. And we saw this very cool example, right? How can you actually apply causal inference to some of these multimodal systems? If you have a question answering data set like this and asking how many zebras are in the picture, and the model happens to give you the correct answer 2, you might ask, is the model actually picking up the treatment variable, actually a counting number of zebras, or is it just picking up some spurious correlation because of the fact that you're asking about zebras in plural is most likely number 2. So we can do is you can intervene on the actual number of zebras by modifying it, by modifying an image by replacing 2 zebras with just 1, by photoshopping out 1 zebra. So that's actually an intervention on the number of zebras by setting that equal to 1. and you find that these models still output the answer 2, which means that the models are capturing some spurious correlations from the question rather than actually counting the number of zebras. And again, this is all about error analysis. Right? Hopefully some of you are doing some sort of error analysis in this form. Causal inference is just a very nice way of formalizing what are the variables you want the model to look at, and what are the variables you don't want your model to look at. And speaking of that, variables that you don't want the model to look at, if you have this question, what color is the balloon? And the model says red, the model says pink instead of red. You might think to yourself, is the model just picking up other objects that look like balloons, but are not actually balloons? So in this case, the umbrella, which happens to be pink, is the confounding variable that affects your prediction of balloon to the actual color of balloons. So to test whether your model is actually picking up these irrelevant objects, you can basically, again, make targeted interventions. Remove the umbrellas from the image using Photoshop. And once you see that, the model actually starts focusing on the balloons instead of focusing on the umbrellas. So again, that's an example of intervention and the fact that the models may not be picking up on the right objects and therefore picking up some other spurious correlations in terms of color. And very quickly, the way this method, this paper essentially contributed all these data set resources, right? Looking at covariant images, so basically images and questions and these counterfactual images that the model should be invariant to, right? Removing should be covariant to. That means the model should be sensitive to the changes in these target objects, and also pairs of objects and questions, images and questions, which the model should be irrelevant to. So basically removing the irrelevant object, and the model should be invariant to changes in the relevant object. And what you can then do is basically do data augmentation, right? And in both cases, on the first side, when you want the model to be sensitive to these changes, apply an objective function to make sure that your model's output changes with respect to this pair of objects. And for the other case, for the pair where you want the model to be invariant, where the answers should stay the same, you can also start regularizing the output to make sure that model outputs actually stay the same for both cases. And after class, some of you are asking me for more resources. And I think this is a very good resource. Judea Pro did more of the initial work in causality through the lens of graphical models. And nowadays, there's many groups. I think there's one of the very big groups working on the intersection of causal inference and deep learning. And this is a nice flowchart they show, right? Essentially, first of all, you know the correct DAG or directed acyclic graph that shows the causal structure. If you do is more causal reasoning, right? If you know that X causes Y, or there's a counterfactual Z that causes both X and Y, you can start intervening in your data to actually reason about these causal factors. Again, just the joint distribution isn't enough. You have to do some form of new operations or interventions. On the other hand, you might also just not know the underlying DAG at all. You might not know, for example, the fact that the zebras cause a prediction, or the fact that a balloon could have been a confounding variable to the actual color. So if you don't know the underlying DAG, you probably have to learn it. Right? And if you want to learn the DAG, it's a very difficult problem, typically NP hard. You got to make some assumptions. And if you're willing to make these assumptions, you can start doing all the work in causal discovery. And if you're not willing to make these assumptions, then you probably won't have really good provable guarantees. So you get more empirical insights, although you won't get the official theoretical guarantees. So again, causal reasoning and causal discovery are two big areas of research. Not really explored in multimodal case, so also open research questions there. And if you don't want to make all these assumptions and you don't know the underlying causal DAG, you can get some empirical results, but typically you can't get provable guarantees on causal inference. And finally, this is another nice figure I really like. We saw this ladder. The first rung of the ladder is just picking up associations. That's where most of supervised and unsupervised deep learning is. Just looking at data and picking up the associations or correlations within a data. The second rung we've talked about a little bit. That's called interventions, right? And we saw that interventions can't really be inferred just from the joint distribution of data, but you have to actually intervene on some random variables, and that may be very difficult. And there's more rungs above it where you can't even intervene, and it's called counterfactuals. But given that interventions are so hard to achieve, is there something in the middle between just association, which most of deep learning is currently doing, and actual interventions? And what this group positions their work is they call this rung 1.5. In the middle of association and interventions, they call it causal deep learning, where you still want to use deep learning to capture good associations from your data, to learn features. At the same time, you want to use some ideas from intervention, although you can't do intervention exactly. And essentially, you get this intermediate step, causal deep learning, where the ideas from causality, even though you can't do exact intervention, can still help you in many, many different settings. And some of the cool settings include, for example, distribution shift, fairness, data augmentation, and so on. So this is kind of a rung where you can kind of do some theory. You can also get really good results because you're combining with deep learning. Again, more references here. So that was it for inference. Inference, taking different elements and learning the right way to combine these elements. We saw it just combining using deep learning methods through dense layers. We saw combination using logical inference, and by extension, differentiable ways of integrating logic into your models. And I just did a quick recap of causal inference, which we talked about 2 weeks ago. And again, all these don't come for free, right? All these causal DAGs, direct acyclic graphs of your treatment variables and your confounding variables don't really come for free. So the fourth sub-challenge is that of knowledge. How do you actually leverage prior knowledge or domain knowledge to learn reasoning? So again, a lot of the work that we've seen was more on domain knowledge, right? You have domain knowledge for the problem. How do you define the right structure for reasoning? How do you define the right intermediate concepts for reasoning? How do you define the right inference paradigm for reasoning? These are all from domain knowledge. And again, domain knowledge is perhaps the biggest driver in this research field. Or there's some other work also on knowledge graphs and other forms of unstructured knowledge. And again, I can't do this whole field justice, so I'm just going to go through very quickly in about 5 to 10 minutes, some examples of using unstructured knowledge to help us do reasoning. So the whole idea of external knowledge is based on the fact that knowledge can be gained from external sources. Just having a data set, a supervised data set, isn't enough for you to contain all the knowledge you want to solve your problem. So one example of this very cool data set back in CVPR 2019 on a new visual question answering benchmark that requires explicit external knowledge. So one example from this data set is this image, and the answer is, what kind of board is this? Right. So to answer this question, it's typically going to be quite hard to do it just from supervised training examples. So it requires some amount of knowledge of what water sports are, what sports equipment are typically used in water sports, and so on. And the existing models typically struggle a lot when external knowledge is needed. So some of these methods essentially integrate external knowledge. One very cool paper is integrating external knowledge from Wikipedia, right? Wikipedia is a great source of unstructured knowledge that contains all the information you want about water sports and sports equipment and so on. So essentially what you can do is take this image, run an object detector that detects the main objects within the image, and perform some amount of retrieval with respect to Wikipedia. So again, the retrieval here, I'm not going to go into the details, but it can be formalized as representation coordination, right? Making sure that whatever objects you detect in visual representations are aligned with different text entries in Wikipedia. And you can do this multiple times, right? The first time you can detect an object, it may be something like a wakeboard boat. And Wikipedia tells you that's a boat designed to create a wake. And then you might be curious, what's a wake, right? You can search on Wikipedia for wake and wakeboarder, and that tells you more about the types of people which perform these sports and what the rules of these sports are. You can also detect some other types of similar water sports like kite surfing, skiboarding, and board sporting. And once you have all these individual pieces of information, you can then compose them. This can be seen as individual local multimodal evidences. This can be seen as alignment, and this can be seen as a composition, the reasoning. And in this case, the reasoning was rather simplistic. It was just using a language model to heuristically compose all these individual evidences and give out the right answer. And if you train with supervised learning enough your language model, you're going to get a reasonable answer extracted from all these evidences. But this is one example, right? And a key idea here is that Wikipedia and other sources of external knowledge can also be seen as a modality, right? Beyond the typical modalities, like your image and question we typically reason about within these question answering data sets. So in some sense, it's almost 3 modalities, right? The image, the question you're asking about the image, and this external source Wikipedia, which are all doing local representation learning and also representation alignment over. One other cool work, just to talk about really quickly, is the creation of multimodal knowledge graphs. Right? In the previous case, we saw external knowledge from Wikipedia, that's largely text-only source with perhaps a couple of images per website. You can also build a more explicit multimodal knowledge graph to help you use external knowledge. So this paper, back in 2015, designed this very large-scale multimodal knowledge graph. You can see some of these nodes are images. For example, there's some cathedral. And some of these other nodes are based on natural language. And between every pair of nodes, you have some joint distribution. That's your affinity function, basically telling you how likely a joint distribution is of this image with this other text node. And you can see that maybe some high nodes indicated as natural light in this image, that this structure is man-made, that this structure is a basileia, that is outdoors, and is for religious services, and so on. So again, these are examples of external knowledge in the form of multimodal. They can also use to start answering these questions. Right? Let's say you have a new image come in, and you want to reason about what this image is used for, who would typically use this image, and where it's typically located. So you can start putting this image into your knowledge graph. Again, this is all representation alignment. You align the representation of this image with representations of your nodes in your knowledge graph. And once you can do that, you can start looking at nearby nodes within this knowledge graph that tells you what these objects are used for. So you can do very nice inference like this. You can get your affordances. You can know that this is a auditorium, is used for community and social work, is required for taking classes, might be used for watching the performing arts, and so on. So again, these concepts, again, in the form of reasoning, the concepts are interpretable. The concepts are all based on natural language, either in knowledge graph or in reasoning across knowledge graph. The structure is multi-step inference. You can look up into the knowledge graph multiple times, as many times as you want to get enough knowledge. And the composition is graph-based. Composition is going through a graph, looking at what is nearby nodes within a graph, and then propagating nearby nodes stored within a knowledge graph. There's a lot of open challenges here. I think Yang has been doing a lot of really cool work in external knowledge graphs. There's some very large knowledge graph collectors that can be used for multimodal inference. This is a cool example of if-then common sense. Essentially, all these games where if something happens, what should I do afterwards? There's also several other examples of knowledge graphs, like moral knowledge graphs. For example, can you actually build an explicit knowledge graph that says we should treat different genders equally? It is rude to judge people based on their appearances, and so on. And it's also knowledge graphs of social common sense. For example, you should let the authorities know when you are in danger. You shouldn't make trouble late at night, and so on in your neighborhood. So again, a lot of the work in knowledge graphs is about firstly collecting all these good examples of data. And you can look at these papers to see how exactly they call these examples. And the other big part is perhaps using them for your research projects. Again, lots of cool references from Yejin's group at UW. And I've also listed some of the references over here. So to summarize about reasoning before we go to generation, we've seen local representations taking individual elements across both modalities and learning a representation across them. We've seen an alignment that takes into account multiple elements across multiple modalities and taking into account all of the connections between all elements across all modalities. Given all this information, reasoning is all about combining it in the right way, in a principled and robust way to best learn your prediction. And we saw some amazing motivating examples of reasoning from this winter ground data set. That one case, which is happening really often in the real world, such as looking at the image and captioning some plants surrounding a light bulb, that's very easy for current models, but just switching apart some nouns within a caption makes it very difficult for existing models, right? Existing models, no matter how much data you train on, all perform just at random chance. So reasoning was all about composing them in the right way in order to generalize beyond those compositions seen in the training data. And we looked at structure, the individual parts, and how do you combine these individual parts in the right way, in this case, a subject, verb, object structure. The concepts that define the intermediate concepts between image and text, such as what a plant is, what a light bulb is. The inference, which is the relation of how you should combine these individual concepts. In this case, surrounding is a spatial relation. And finally, all this is not possible without domain knowledge from humans. And with this structure, just a quick recap, single step structure is everything you see kind of before reasoning. It's using neural networks to combine data in a single step. In reasoning, we looked at multi-step structure, In the case of temporal structure, where we looked at memory models, hierarchical structure, where we looked at tree and graph networks, interactive structure, where we have a couple of lectures on reinforcement learning in order to best optimize long-term rewards, and structure discovery, where we kind of extended some ideas in reinforcement learning to do optimization of our discrete structures. In concepts, everything before reasoning was just dense neural network concepts. We looked more at slightly more interpretable concepts based on attention maps, and even more interpretable concepts based on hard attention and perhaps even language. For inference, to combine these concepts, everything before, again, was just based on dense representation, but you can also do logical and causal inference. And all of this is not possible without either domain knowledge from humans or external knowledge from, example, multimodal knowledge graphs or Wikipedia. And that's all for reasoning. A very big challenge. Took us about 3.5, 4 lectures to get through it. But any questions beyond reasoning before we go on to generation? Typically, I would. And again, modality is all about two things, right? The heterogeneity within the modality and the interconnections across the modalities. So knowledge graphs and other terms of external knowledge like Wikipedia typically have their own dimension of heterogeneity that you want to account for. It's not the same as text. It's not the same as natural images, audio, time series, and so on. So you want to account for those unique dimensions of heterogeneity. So a lot of the works that integrate external knowledge typically design some specific form of model that allows you to, for example, traverse a knowledge graph or look up across multiple steps the knowledge graph. And the second thing is our interconnections, right? The alignment, the connections between the modalities. And again, that's also going to be quite different, the connections between your data and the knowledge graph entries. So typically, it always helps, instead of reasoning about whether it's a modality or not, just reasoning on this spectrum, the different dimension of heterogeneity in this modality and a different dimension of interconnections that might exist with knowledge graphs. And again, a lot of open challenges in reasoning. This is perhaps one of the sub-challenges that is studied relatively less as compared to representation and alignment. In structure in general, multi-step inference is always much harder than single-step inference. For concepts, it's a big area of research in how do we combine interpretable and also, differentiable representations. In composition, a lot of the work in, for example, causal, but also multi-step structure with interpretable concepts, all this wide space beyond a single point is relatively unexplored. And finally, knowledge, right? We have all these large pre-trained models nowadays. They definitely contain some amount of external knowledge, although it is quite unstructured and really black box, right? How do we kind of probe these pre-trained models for the reasoning capabilities is a big area of work. Cool. Now generation. So in generation, the whole idea is to generate more multimodal data. How do we take representations or data that we already have and produce raw modalities that you can use visually in the real world? But there are some constraints on these raw modalities. We want to make sure that they still respect the interactions with other modalities that you're generating at the same time. You want to make sure that they respect their own structure and that they're coherent. So all the different dimensions of heterogeneity that you've seen, when you generate these modalities, they must also respect these dimensions of heterogeneity. And there's three big things. One is summarization. Can we take in more multimodal data, such as videos, very long videos, and summarize it by keeping the most salient information? In this case, taking all these videos and summarizing perhaps just one image in a video or perhaps a caption of the video. Another big area of work is translation. Can we take in one modality, for example, and translate into some other modality while maintaining all the interconnections between these two modalities? For example, taking an image and describing the image fully in natural language. And the third one is that of creation. Can we take in something smaller, such as latent variables, or perhaps just one image, and generate more multimodal data that respects coherence? So you can't generate multimodal data freeform, it still must respect the coherence. So for example, can we take a latent variable that represents the idea of a beach and generate images of things on a beach, descriptions of big dog on the beach, and sounds of what you typically hear on the beach? So that's expansion. And although these three are, you can think of them as sub-applications, there's always two core dimensions in generation. One dimension is just how the information content changes. And we've seen that already, right? Can you reduce the information content, maintain the information content, or expand the information content? But underlying the information content is basically that of interconnections, right? All the content that we're looking at across modalities We basically want to answer how these modality interconnections change as we do generation. Right? Do the interconnections reduce? Do we look at the most important interconnections? Do we try to maintain all the interconnections when we want to translate from an image to text, for example? Or do you try to expand and generate more cross-modal interconnections than what we started with? And just to recap, because this was from the first lecture, modality interconnections basically describe, given elements across modalities, the ways that they can be related. They can be related from a statistical point of view, purely from data. And if you have domain knowledge, you can reason about semantically how they relate to each other. And again, there's two levels in both statistical and semantic. The first level is just the fact that they associate or refer to the same underlying object in terms of correspondence. And the second level requires some form of inference, such as the fact that one depends on the other or one is used for the other. So again, a lot of work in generation operates under the assumption that there are interconnections in your data, and we can discover these interconnections in your data as we do generation. For example, image captioning is all about capturing the corresponding interaction, looking at images of a laptop, for example, and generating the fact that this is a laptop and what it can be used for and what type of room it's in and so on. It's all about capturing these interconnections. The second dimension is typically a generative process. Given that you've encoded your data, you've captured the interconnections, you've decided whether to reduce, maintain, or increase these interconnections. How can you actually decode it into high-dimensional multimodal data? In a decoding process, you typically want to respect all the dimensions of modality heterogeneity. Right? Whereas in representations, it was about encoding the heterogeneity from data to representations. The generative process goes the opposite way, going from representations to your data while respecting these dimensions of heterogeneity. And again, there's two big paradigms. One is more example-based. If you have a dictionary of translations that you store from your training data or from external knowledge, you can reference this dictionary when you want to generate a source to a target. The other typical approach is our generative models. If you have a dictionary of translations, typically in your training data, you can learn a generative model to parameterize this dictionary of transformations, and then you can apply this translation model onto new data that comes in as a source to try to predict the target. And again, the key point is that you want to respect the dimension of heterogeneity, right? The fact that different modalities typically exhibit different qualities, such as their structure, their internal elements, the different noise in each modality, and so on. So I'm going to go through all these three cases, translation, summarization, and generation, creation really quickly. I'm going to contextualize them in the case of our two dimensions, how the information content changes, and also how the generative process is typically done. So I'm going to start with translation, although that's not the first one, that's the one in the middle. But translation is typically the one that we all resonate with the most, right? So most of us have typically seen, as a motivating example, most of us have typically seen these really cool text-to-image generative models recently. There's called a DALL-E model, and they recently had extensions like DALL-E 2. But the main selling point of these models is that if you can take a text caption, such as an armchair in the shape of an avocado, there's some nonsensical text caption, you can still generate through a generative model, a translation model, really cool images that represent this natural language. So how is this done? So at a very high level, I'm going to go into more details in this lecture and next lecture. What they first do is they train a discrete VAE. And you can train this discrete VAE using just image data. And you can collect a bunch of images, train an image encoder from image into representation space. And this representation space is discretized. That's why they call it a discrete VAE. We'll see what that means very soon. And from this discrete space, they can then train an image decoder to actually get you the output image. So first pre-train this on lots of image-only data. But image-only data is not enough, right? You want to learn this conditional transformation from text to image. So you're always going to need some compared text and image data. So given enough captions from the internet, they can take in text, encode it through a text encoder, transformer, whatever you want to pick, learn a sequence of representations from this text encoder, and learn a mapping from the text representations into image representations. And can do this autoregressively using an autoregressive transformer. And finally, a generation happens here, right? Given a new text example, encode it into a text encoder, learn the text representations, translate it over to image discrete representation space, and use the image decoder to actually generate your image. So again, 2 dimensions. The first dimension is how the information content changes. And in this case, you're maintaining the information content, but what you're doing is capturing these corresponding cross-modal interactions. Whatever is happening in text, you want to represent it exactly in image. And you did that using supervised translation. And how did we do the generation process? This was in the middle of exemplar and generative. Exemplar because you're learning a discrete codebook. That's basically a dictionary of transformations that remembers the examples you've seen during training and try to recreate these examples during testing. And once you have this discrete codebook, the next step is to do a generative process to actually get the actual image. Right? So from information content, it's maintaining content by doing supervised translation using paired data. And the generation process is a mix of both exemplars in the representation space and generative in the decoding space. And then probably some of you have seen DALL-E too, right? Much better results, at least being able to generate cooler images of higher quality. What was the main difference? 3 things, right? First of all, they use a clip encoder, right? Clip, as you know, back from representation alignment, was pre-training a lot of image and text pairs, right? So taking these images, you're not just training this image encoder, decoder, independent of text. You're using an encoder that already brings it into text and image representation space. Right, so using a clip encoder gets you an image embedding that is already pretty close to text space. For the text side, they use a text encoder. They use something fancy called diffusion model to translate it from text to image space. Diffusion model is going to go into more detail next on Thursday. And finally, the generation was also done by a diffusion model. So this, it was found that diffusion models, which are a class of generative models, generate images of higher quality than variational autoencoders, which is the first iteration. And again, all these examples, diffusion models, variational autoencoders, we're going into detail this week. But the underlying principles are the same, right? You first look at how the content is changed or maintained. And in this case, content was maintained by clip similarity. Clip was the bidirectional model that captures the correspondence between text and image. And again, that maintains information content by capturing corresponding cross-modal interactions. And for the generative part, it was a fully generative model using diffusion models that generated these embedding layers to your actual image. So second case study, summarization. So in summarization, the goal is to take something much, much larger, like a very, very long transcript, paired with a very long video, and obtain the most important summary of the long text and long video. So as you might have seen, a lot of the big work here is, first of all, collecting good data sets of this. How can you collect very large video data sets with very long text and very long videos, and also annotate it for the summary? So this how-to video data set is a very good example of this. They collect a bunch of videos. They're essentially these instruction videos with the transcript telling you how exactly the person is doing these things in the video. And they also annotated the summaries from human annotations. So what's happening here is that you're taking in very high-dimensional data. You're learning the cross-modal interactions. And these cross-modal interactions are complementary. They're not just corresponding to each other. So one example is that you're going to take the transcript and summarize it. You can take also the video and perhaps caption it in some way. For example, capturing the fact that it's a pre-burnt breakfast and that it's a free cooking video. And these are not present in text, right? So you have some summary from the video, you have some summary from the transcript. Both are complementary to each other. They don't exactly represent the same amount of information. And then you're combining it to actually obtain the final summary. The final summary is a function of both summarizing a transcript and summarizing a video. And again, abstracting away from this concrete example, you have 2 dimensions. How the information content changes and what generative model you're using. How the information content changes is that you're learning a joint representation via fusion. You're taking in all these multiple elements across modalities on both sides, learning a shared representation. And essentially, this representation captures complementary cross-modal interactions, right? It captures information from the first one and also information from the second modality. Once you've done that, you've learned this representation. The generation process essentially takes this representation and decodes the summary word by word. That's a more generative approach. And you can also think of a more example-based approach, and that's called extractive summarization, where instead of generating a summary word by word, you're actually extracting important words from the text to summarize it and extracting important frames from the video to summarize it. In the last case study, creation, right? We've seen translation to maintain information content. We've seen summarization to reduce information content. creation is all about taking latent variables, or perhaps a set of latent variables, and generating higher information content, generating more multimodal data. So there's many things you can start with. One latent variable, factorized latent variables that represent different concepts, perhaps images. And can you, for example, generate images in the sequence that they should be generated, generating multiple frames to create a video? Can you generate long amounts of text where each sentence or each phrase is coherently dependent on the previous sentences? And can you also generate audio that corresponds to the text description and video descriptions? And again, just like all other challenges, the main goal of creation, one big challenge is that maintaining that the cross-modal interactions are coherent with each other. Whatever you're generating in image space should be aligned with what you're generating in text space, and should be aligned with what you're generating in audio space. So auto work and alignment is important here. And again, if you want to generate more data than you started with, you got to make sure that the data you subsequently generate is coherent in itself, right? It should be temporally and causally and logically coherent. So again, recall all the works in reasoning and recall all the works in making sure that these modalities respect their own dimensions of heterogeneity. But creation is very difficult, right? I don't think there's any work that is able to generate images across a long video, together with text that describes the video, and together with audio that is representative of the video. But there's been some initial attempts. And a lot of these initial attempts start with not just one latent variable, but a set of factorized latent variables. And factorized latent variables are useful because you can tell what each latent variable is supposed to do, right? In this case, you could perhaps hit up a latent variable that just represents the first modality, one latent variable that represents the second modality, that's ZA2, and one latent variable ZY that represents the joint information across modalities. So then you could start plugging in these latent variables into decoder models, and we're going to show you how to train them in this lecture. And this decoder can essentially help us generate images, right? The first latent variable, ZA1, tells us how to generate images in one particular style. And ZY, the joint latent variable, tells us what exactly digit I want to generate. So given the same ZY telling me what digit I should generate, and some other ZA2, some other style variable, I can then generate the same digit in some other style. And if I just want to use the joint latent variable representing a digit, I should be able to predict that a digit is actually 9. Right? So essentially, ZA1 and ZA2 are your factorized latent variables representing a unimodal structure, the uniqueness within each modality. And ZY is your joint latent variable representing the interaction, the shared commonalities across both modalities, the fact that they're both digit 9. And with these latent variables, you can then do some amount of creation. You can then do, for across two modalities, one SVHN, so digits in a certain form, and another modality MNIST, digits in some other certain form. You can fix the latent variable representing the digit. You can get 5s in different styles, and also 5s in different styles of the other modality. You can fix the latent variable representing to the style of the first modality and get multiple digits in the same style. And you can also fix the style of the second modality and get multiple digits 0 through 9 in the second fixed style. And this is not exactly perfectly creation of videos and images and audios, but it's some initial attempts. Right? And the main idea, again, 2 dimensions, how the information content changes and what generative process you're using. So in this case, the information content use a fission representation or a factorized representation, taking in 2 modalities and learning more representations that you started. Right? And this is really helpful because then you can now more controllably generate data according to the variations in each of these latent variables. And the information content is expanded because you're taking in these complementary cross-modal interactions, your ZY, representing the common style, the common digit, and generating more data across different styles. And finally, a generation was done by a VAE generative model. So all this was a preview. Looking at some case studies, we've seen summarization, translation, and creation. Look at case studies of how the information content changes, either reduced, maintained, or increased. And we also mentioned how the generative process is actually done. We've seen some keywords like VAEs and diffusion models. We're going to go into all these details in this lecture and next lecture. But again, as part of the preview, before going into the details, a lot of the main challenges in generation, of course, are actually generating high dimensional data. How do you do that with high fidelity? But another big challenge is how do you actually evaluate these models, right? I want to touch upon this before I actually go into the methods of actually generating data, because I want everyone to be aware of these evaluation challenges and ethical concerns when we're actually generating more data. So there's some very big challenges. How can we generate, for example, modalities beyond text, image, and video? There's a very understudied subject. How do you translate between descriptive text and images? Typically, translation requires you to have very exact pairs of images and captions, where the captions describe exactly the image. Can you generate something that's more corresponding? For example, generate facial gestures while at the same time that I'm laughing or saying some positive word. Not exactly referencing each other, like images and captions, but just the fact that these different sensory modalities happen at the same time. And finally, creation is, of course, very difficult. But more importantly, there's huge challenges with evaluating this content, right? Should you use human evaluation? Are there good ways of doing automatic evaluations? That's also very difficult. And also ethical concerns, right? We've seen that these generative models very easily pick up biases in your data. For example, this generative model that was claimed to upsample and increase images of resolution turned black person white. Some examples of these language models that are able to generate text are also able to memorize text that you've seen in your training data, and as a result, regurgitate sensitive information like social security numbers, phone numbers, and so on. And likewise, all these language models are also sensitive to generating biases about different race and genders. So just all these are ethical concerns that you should be aware of when you're actually using these generative models or designing these generative models. And of course, open challenges. How do we kind of evaluate and remove these biases, quantify and remove these biases from these language models, or in general, generative models? So now going to the details. Generative models, right? So the whole idea of generative models is to model P of X, where X is some data that you've seen, could be text, images, videos, multimodal data. And the whole idea is to have a good estimate of P of X for two things. Given a sample X, can you evaluate P of X? That tells you how realistic one sample is. I also want to sample new P of X, right? Far higher regions of P of X of high density. I want to sample more. That gives me more realistic images or text or other data. Lower regions of P of X, I should sample less. And typically, generative model is also useful, not just for generation, but also for unsupervised representation. If you can learn a good model of P of X, you can also start conditioning this model to get P of Y given X, like fine-tuning your generative models representations on some task. So all of generative learning is about learning P of X. Sometimes we also care about P of X given C. Let's see, it's a class variable they want a condition on. Typically, X given C is more useful because you want to be able to control what you generate, right? C could be some prompt you give to a language model. So you generate some output condition on this prompt. C could be some style, for example, a painting in a certain artist style, and so on. Typically, you want to do P of X given C. Sometimes you also want to care about P of X2 given X1 and C, right? Given some input data X1, and given some change in style, can I generate the same data, roughly the same, but only sensitive to these changes in style? For example, if I give you an image, already some painting, so just go to the bottom left corner, that's my X1, and I give you a C representing a certain artist I want this style in, can I generate the same image in the same artist style? Or in style transfer, if I give you some sentence X1 and some style change, for example, C is a binary variable representing positive, negative sentiment, I should be able to express the same form of text with only a sentiment being changed. So a lot of these generative models are based on latent variable models, right? The whole idea of latent variable models is that you want to learn a generative process from latent variables to observe data, and you can design these latent variables however you want. Typically, these latent variables are going to be disentangled and factorized in some form to represent the fact that generating data, the data that you generate should depend on multiple latent variables, right? So for example, if you want to generate human faces, one latent variable you want to generate perhaps is their age, whether they're wearing glasses, whether they have long hair or short hair, and so on, whether they're wearing a cap and so on. So all these different controllable factors that you want to generate can be seen as your C's. They can also be seen as the underlying latent variables in these latent variable models. So over here, with these images, you have a bunch of, for example, disentangled latent variables representing gender, eye color, hair color, pose, and so on. And the main challenge in latent variable models is that you observe your data at the data level, you observe all your X's, but you typically don't observe all your Z's. Your Z's have been learned. And there's some very initial attempts of learning these, right? One general recipe is that you can go Bayesian. You can first put a prior on Z. Let's say Z is just a normal distribution. So for example, my eye color is a Gaussian distribution between 0 and 1. 0 represents one color, 1 represents other color. 0 to 1 just interpolates. Again, you can have 0, 1, the length of your hair. 0 is a short hair, 1 is a long hair. 0 to 1 interpolates. And then you can start, given the Z's that you sample, how do I essentially learn a P of X given Z? How do I transform my latent variable Z into my actual data X? And P of X given Z can be very expressive. It can be done through neural networks and so on. That perhaps is some distribution taking into the Z's and through some parameters, mu of theta and Z of theta, where there's these parameters are neural networks. And one very simple example of latent variable model, before we actually go complex, is mixture of Gaussians. Most of you have probably seen mixture of Gaussians. You can define Z as a categorical distribution. That tells you which cluster you are in. And for each of these clusters, the fact that P of X given Z is some cluster K is some Gaussian centered around that K cluster. And the Gaussian's parameters, the mean and the variance, can be learnable, right? So it's mu K and sigma K can be learned depending on different cluster centers. So then your generative process, and this falls in a generative model, this can work also really well, is the first big cluster, which we call a mixture component. It can be either soft or hard. So hard just picks one cluster. Soft picks multiple clusters weighted by some weights. You can first pick a mixture component by sampling a particular cluster. And given that particular cluster, you can then go to the Gaussian representing that cluster with that Gaussian's mean and variance, and then you can generate your data from that Gaussian. So given some form of weird real-world data distribution that is very multimodal in nature, you can start fitting these Gaussian mixture models by essentially first deciding a number of clusters and where the clusters are, and also learning the mean and variance of each cluster. And these methods are all about maximizing likelihood, right? How can we write down P of X, which basically tells me how well I'm describing my data. I want to maximize my P of X, basically learning a distribution that highly corresponds to the data that I actually observe. And P of X can then be seen as summing over Z, where Z are my latent variables. In this case, the cluster centers. Summing over Z, P of X given Z. And the fact that it decomposes where my joint distribution of X and Z corresponds to first sampling Z, my cluster centers, which cluster it is, and then P of X given Z, given which cluster it is, or the actual parameters of that cluster. So that's the Gaussian corresponding to the actual cluster. And this final distribution can be seen as P of Z given K. So that's a categorical distribution telling you a prior over which cluster centers it is. And also the mixture component telling you what distribution of that cluster actually generates my data. And mixture of Gaussian is simple, right? We can solve this using expectation maximization. For example, taking your data, first inferring which clusters it is, and fixing the cluster centers, and then inferring the parameters of this cluster and recursing, right? So essentially taking into account learning your P of Z given K, and also learning your mu K and sigma K iteratively. And the first extension, and we're going to talk about VAEs first, the first extension is from Gaussian mixture models to variational autoencoders, right? And there's not actually much difference, right? In variational autoencoders, you also have a prior Z. It can be Gaussian with mean 0 and standard variance. It's just that when you're learning Z to X, you're taking these latent variables Z and generating X, it can be much more expressive, right? You're basically defining a neural network parameterized with this latent variable Z with some mean vector, mu of theta, and some variance vector, sigma of theta. With your theta can be your neural networks, and your mu of theta and sigma of theta can be very expressive, right? And the hope is that after you learn this model, you have data X, you try to learn your latent variable Z, that's your training. You can then take these latent variables Z and try to generate more data X. And even though P of X given Z is quite simple, it's just neural network from Z to X, the marginal P of X, which integrates over all possible cases of Z, can be very, very expressive. So how do you learn this, right? The whole idea is to learn this underlying distribution across both your input data X and your latent variable Z. So the setting is that you have a data set D, where for each data point, you just see X, right? X can be the text or the image that you want to model using a variational autoencoder, and Z are not observed. Z are latent variables. And if you don't know, and if you want to maximize the likelihood, you want to learn a parameter of theta, what you can typically do is just to maximize the log likelihood. The log likelihood of a product over all samples in your data set, P of X given theta. That tells me how likely each data point I am going to observe in my data set under this generative model with parameters theta. You can move the log inside, so that becomes a summation across all data points, log likelihood. And then we know that X is not just P of X, but there's some underlying distribution Z, your latent variables generating X. So you want to sum over Z, you're going to join distribution P of X and Z given parameters theta. And typically the issue is that you want to sum it over Z is very difficult, right? In the Gaussian mixture model case, summing over Z was just K possible categorical variables with those K centers. In many other settings, if your Z's are, for example, neural network layers, each with like very high dimensions and very continuous dimensions on each layer, then summing over Z is going to be quickly very intractable. So even if Z is binary, 30 dimensions, you're going to sum over 2 to the 30 cases. And if Z is continuous, the integral over Z instead of summation over Z is going to be very difficult. So if you can't compute this log likelihood exactly by summing over Z, you're going to need some approximations. So instead of summing over Z exactly, it can be approximately sum over Z and still optimize our log likelihood. So the whole idea of variational autoencoders and all these other approximate inference models is to introduce some other distribution Q. And if we can't compute log likelihood of P exactly because summation over Z is going to be intractable, can we introduce some other distribution Q which could be simpler, right? And then you can start thinking, right? What distribution should I introduce, right? Ideally, the intuition is that Q should be simple. That you can sum, you can compute the log likelihood, you can sample from very easily. But at the same time, Q shouldn't be that much different from P. Right? If P is like super expressive and hard to measure, and Q is some simple Gaussian super far away, you can optimize over Q, but you're not going to be anywhere close to optimizing your actual log likelihood. So the trade-off, right? Q should be a simple distribution. You should be able to approximate and compute a log likelihood and sample from it. But at the same time, you want it to be close to the actual P that you want to measure, which is the log likelihood of your actual data. So how can you then formalize this trade-off, right? So the whole idea of kind of evidence lower bound variational inference in variational autoencoders is to formalize the fact that how can we choose a good Q that is simple enough for us to learn, at the same time close enough to the actual data distribution P. So this slide perhaps tells us the big, most important equations, right? You have a log likelihood of a data, with a log of the summation over Z's, which is intractable, and a distribution P of X and Z. That's a joint distribution of our data and latent variables. We're going to introduce Q of Z over Q of Z on a numerator and denominator that cancels to 1. And once I have this, if I have a summation over Q, a summation over Z, Q of Z, that's basically an expectation over Z, right? Definition of expectation. So I have an expectation over Z, and what's left in the expectation is my P over X and Z over my Q of Z, right? The real log likelihood of the data over this some other simple distribution that I've defined. But now if it's log expectation term, right? Expectation is how a log, I can't really do anything about it. What you can do is you use transience quality, which basically says for concave functions, where concave is this shape. The actual function lies above the midpoint of 2 points on the curve, right? So the actual function, which is a curve, is greater than or equal to the linear bisector across 2 points under the curve. So what you can do is you can bring the log inside, your log of expectation under Z, you can bring that log inside, and you can basically upper bound that by a summation over Q by log of F of Z. And it's not going to be exact because you can't actually bring the expectation inside the log, but you're going to get a lower bound. So when you apply it to our distribution, you can bring a log inside the expectation. What you end up with is a lower bound expectation over your Z under your simpler distribution Q of Z, log of this ratio. Your likelihood ratio of the true data under your true data distribution P over the simpler distribution that you've chosen Q. And this is actually called evidence lower bound, right? It's a lower bound because you've done Jensen's inequality on the concave function, your expectation, and evidence because you're still trying to approximate a lower bound to the actual evidence data distribution of your real data. Continuing, we know that our log likelihood can be lower bounded by an expectation over Z. So that's summation over Z, Q of Z, and the log likelihood of our ratio. we can factorize this. Log A over B is log A minus log B. So that gives you my expectation of the Z, the log likelihood of my actual data, minus the entropy of Z, entropy of Q. And entropy of Q is essentially the expectation over Z log Q of Z. And this gives us a very nice lower bound, right? The real log likelihood of my data is equal to the expectation under our simpler distribution, how well my data fits a simple distribution, plus the entropy of my simple distribution. So if I choose my simple distribution to be exactly the same as my real distribution, then you have equality. There's no lower bound. But the whole idea is that you can't actually maintain this equality because your real distribution P is very difficult. Q should be a simpler distribution. So you want to choose Q of Z to be as close to P as possible while being easy to compute. So the measure of closeness can be formalized by KR divergence. Some of you have probably seen this KR divergence. The KR divergence between two distributions, Q, the simpler one that you want to choose, and P, the actual distribution, can be written in this form. An integral over Q, log Q over P dz. And the KR distribution is a very nice case, very nice intuition, right? Essentially, P is a hard distribution, Q is a simple distribution. If my Q is low, then I don't really care. So if my Q is like whatever target distribution that you choose, Q, if that is low, then the expectation Q of Z is going to be low. You don't really care how far Q is away from P. So you only care about the cases where your simple distribution Q has high density. And for the cases where the simple distribution Q has high density, you want it to fit P as much as possible, right? Any difference between Q and P is going to incur some error. All right, so essentially you're going to get a graph like this. Your P can be very complicated. It's very, very bimodal distribution with a lot of peaks. And Q is a very simple distribution. It can be a Gaussian. You only care about the cases where Q is high. Where cases where Q is high, you want it to match P exactly. Where the cases where Q is low, like so these other areas, you don't care about what the divergence is. So the intuition here is again the fact that Q can be very simple, right? Q doesn't need to cover all parts of P. But for the parts of P that Q covers, it should cover P exactly. So you can actually also rederive this evidence lower bound from this KR divergence, right? So it essentially brings both ideas together. You can either rederive the evidence lower bound from Jensen's inequality to lower bound the actual log likelihood of your data, or you can also start from the KR divergence, essentially choosing a Q to minimize the KR divergence between Q and P. So you can write out this definition of KR divergence. This basically follows from the definition. KR divergence between Q and P is an integral over Q log Q over P. You can write this out. The negative expectation over Q log P, the expectation of your actual data under my simple distribution Q, plus log likelihood of my real data, log of P, minus the entropy of Q. And we know as a fact that that KR divergence is non-negative. So if this term is non-negative, you can rearrange this term to rederive the elbow. The fact that my log likelihood of my data is again at least two important terms. The distribution of my real data under this simpler distribution, Q, plus the entropy of Q. And again, equality holds if Q is equal to P, right? Because the KR divergence between two similar distributions is 0, so all this whole thing equals to 0. So in general, that gives us the answer, right? Instead of actually computing a log likelihood of my data, I can write my log likelihood of my data as this evidence lower bound. The likelihood that I'll observe this data using my simpler distribution Q plus the entropy plus some KR term. So the closer my actual guess of Q, which is a simpler distribution, is to the actual distribution P, the closer this elbow is to the likelihood because this KR divergence goes smaller to 0. So that's the whole idea of variational inference, right? You can't compute my real distribution P. I can choose a simpler distribution Q to compute instead. I can parameterize my Q with any parameters that I want. So instead of defining Q and staying with it, I can learn Q as well. So Q, for example, can be Q of Z, given some parameters phi, where phi tells me that it's a mean with some mean parameters and variance parameters. And I want to learn these parameters phi so that my Q of Z is as close to P of Z to an X as possible, while still being simple. So here's a very nice graph for variational inference. On the x-axis, we have our parameters phi. That's the parameters of the Q that you want to learn. On the y-axis, you will estimate of a log likelihood. So my log likelihood of my real data, log P of X, is always fixed. That's the blue line at the top. And across different settings of my parameters phi, my evidence lower bound, which is the evidence that I see this true data under my simple distribution, can change. Right? Some setting of parameters phi is going to give me a higher evidence lower bound, closer to the true log likelihood of the data. Some other settings of parameters phi is going to give us a smaller lower bound. And the difference between what I estimate as my evidence lower bound, given my current setting of parameters phi, and the actual log likelihood of my data, that gap is a KR divergence between Q and P. So given that we've estimated, instead of using the log likelihood of the data and instead converting it to the lower bound, then the question becomes, how can we actually learn these parameters? Or how can we actually learn the Q? We thought we want to learn the Q over these parameters phi, right? How can we actually learn the Q of phi of my Z, and also the encoder, right? How do you actually get from X to Z's? How can I learn this encoder and decoder at the same time? So that basically gives a variational encoder, a variational autoencoder. This graphical model basically shows that you have some data X going from X to some underlying distribution of a latent variable Z. That's called your inference model. That gets you my Z given X. And once you have Z, you can also generate your X. That's your generative model that learns your P of X given Z. So essentially, this is again the evidence. This is the evidence lower bound that you derive. The fact that you want to estimate how likely my data is, P of X given Z, under my simpler distribution Q, minus a KR divergence, telling me how far away my simple distribution Q is from the actual distribution P. So the first term is typically known as a reconstruction. That's basically saying under my distribution of my simple random variable Z, how well can I reconstruct my data? So this should be as good as possible. And similarly, I want my Z to be simple. That basically tells me a prior. I want my Z to be simple, and typically we regularize this prior to be a standard Gaussian. So balancing off two objectives, the fact that your Z, your latent variable distribution is simple, that's your prior, with reconstruction, the fact that your latent variables Z are expressive enough to actually reconstruct your data. So that gives us a general training recipe for these autoencoders. Right? I'm going to take my data X, and I'm going to have a bunch of IID samples. I'm going to take a data point X and map it to Z into the latent variable space. That's the encoding process. That gives my distribution of Z given X. That's the encoder. And once I have my distribution of latent variable Z, I want to make sure that I still are able to recreate my data X. So that's my X given Z. The first part, the encoder, can be seen as inference of my latent variable Z. And the second part, decoding, can be seen as my generative process to actually generate new samples of X, given my distribution of Z's. So given this objective, right, this reconstruction objective based on evidence lower bound, and the difference KL term based on the difference between the evidence lower bound and the actual true observed likelihood, to learn anything, we need to compute the gradients. So you got to compute the gradients with respect to theta, which are the encoder parameters, and phi, which are the decoder parameters. So for the encoder parameters, it's relatively easy, right? The gradient of respect to theta across these two terms. For the KL, it doesn't really depend on theta at all. The KL is just a prior between my decoder and my prior, so this goes away. And my expectation under Q, that depends on the parameters phi, which is the decoder parameter, that doesn't depend on the encoder. So you can move the gradient with respect to the encoder inside. It's not even expectation. Under Q, a gradient of the log likelihood of your data X under Z, right? So essentially, you can learn the encoder very easily just by approximating the expectation over Z with a bunch of samples. So the second one is more tricky. The second one, taking parameters with respect to phi, which are the decoder parameters, is a bit more tricky. And to see why this is the case, the loss function that I have, the expectation is sort of depend on Q of phi, right? That's my decoder parameter is phi. Q of phi tells me the distribution of my Z given my current X. That depends on phi, so you can't actually bring the gradient inside the expectation. But what you can do is do this parameterization trick. So in general, what this trick does is that, let's say you have an expectation under some distribution z, where the distribution of z depends on some parameters phi, and there's some objective that I want to optimize. So this can be written as an integral over z, a distribution over z dependent on phi, some function over z, dz. I'm going to assume that my z is some Gaussian with parameters mu and sigma square. So mu and sigma can be learned. And in general, there's two ways of sampling this z. You can either just sample z from this distribution together, or you can first sample a noise vector epsilon from the standard Gaussian. So this noise vector epsilon doesn't depend on any parameters. And then you can transform this noise vector with respect to multiplying by this standard deviation, adding the mean. You can still get a distribution from this underlying distribution, g of z. So the second one is actually a very nice way of computing the expectation. So instead of actually computing the expectation over z under q of z, rz, I can instead compute the expectation of my noise vector epsilon from random noise, followed by this transformation of this noise vector into my z vector, and then computing the loss on my z vector. So that's equivalent to an integral over probabilities of sampling noise, epsilon, transforming this epsilon into mu plus epsilon times sigma, and computing the loss on R. In that case, the really cool thing you can do is that any gradient that you want to compute with respect to your parameters phi, you can, instead of computing it over the expectation under z, you can compute it with respect to expectation under some noise vector epsilon. And this noise vector epsilon doesn't depend on phi, right? It doesn't depend on anything. It's just standard Gaussian noise, which means that you can then bring the gradient with respect to phi inside this expectation. So I have the expectation over my noise vector epsilon, gradient with respect to phi, and all your things that depend on phi, which is the transformation from this random noise vector into my actual z distribution. And now you can then approximate it using multi-causal sampling, right? Sampling a bunch of epsilons from my noise distribution. That all doesn't depend on my parameters phi, and replacing the expectation over epsilon with respect to an average over all these k random noise vectors that I sampled. And for each random noise vector, I'm going to then transform it into my z vector using my transformation, multiplying by sigma, adding mean, and then computing the gradient with respect to phi, which depends on the mean and sigma. So therefore, what you can do is that you can reparameterize, right? Instead of taking a gradient with respect to phi of expectation over something that depends on phi, underlying distribution q of phi, you can then change the expectation over a noise vector epsilon. If you replace it with epsilon, then all of the occurrences of z inside your expectation have to be replaced by a transformation of this epsilon vector into z. So mu plus sigma z, mu plus sigma epsilon instead of z. So that's reparameterizing. And then you can move the gradient with respect to phi inside the expectation, because the expectation on epsilon doesn't depend on phi anymore. And then you can then compute the gradient of this log likelihood of your data with respect to phi using samples. And very last figure before we go, what we've essentially done is taking an x and a phi. That goes to your z. But now you have a bottleneck layer, right? You can't really backpropagate your gradients from my output f with respect to this sampling layer with respect to phi. What we've done instead is we've broken this up. We've broken this up into my parameters phi, that's my mean and variance, my data x and epsilon noise vector. All of this still equivalently compose z. But now z is a deterministic vector and not a stochastic vector, because all the randomness went into this random noise epsilon. So given this random noise epsilon, you can generate z, get a function f that you want to optimize with respect to, and you can still backpropagate your gradients from the output f through z to the parameters phi that you care about. Okay, I think we're out of time. 11:30, right? Yeah. But thanks. I'm going to recap reparameterization on Thursday, but I think otherwise you're free to go. Thanks.